All right, so this is Lecture 2, Part 2. So we're going to start off with the lecture with a discussion of what is meant by the limit of a function. And usually when we talk about concepts in math, we motivate them using definitions. So let's start off, however, before we get to the definition, with an example. So let's try and solve this particular problem. The limit as x approaches 2 of, say, the function x squared minus x plus 2, okay, which is a parabola. Oops. Try it again. X squared minus x plus 2, right? So we want to evaluate the limit of this function. So that's our objective. So what if we were to look at the graph of the function? So let me pull up the graphing calculator. So we have y is equal to x squared minus x plus 2. All right, so it's this parabolic looking shape. All right, and we want to know what happens to this function as x approaches 2. So here we have x equals 2. The line x equals 2 is shown in blue. Right there. And then we have the line y equals 4, which is shown in green. Right here. So we anticipate that as we approach x from values of x less than 2, that the output would be 4 right here. And by a similar strategy, as we approach 2 from numbers bigger than 2, from x values bigger than 2, we anticipate the same output, which is 4. Okay, so we can summarize this result using a tabular approach. So let's try using a tabular approach. So let me insert a table and show you, and let's examine the numerics of a table. So bear with me while I insert the table. Okay, so consider this table. So it's a multi-column table. This table has a divider, and in the left two columns we examine the limit analysis as x approaches 2 from values of x less than 2. So you see we start off, say, at x equals 1, and we increase 1 all the way up to, but just shy of 2, because that's what the limit operator stipulates, that we can never hit 2, but we can get close to 2. So we're approaching 2 from the left, right? And observe the output values. Okay, the output values increase steadily, and finally they approach to the upper bound of this sequence of outputs appears to be 4 from the left as we approach 2 from the left. Likewise, if we look at values of x as we approach 2 from numbers bigger than 2, see how we're approaching 2 from numbers bigger than 2? Look at the sequence of outputs. The sequence of outputs appears to have a lower bound of 4. Okay, it appears to settle on a converging value of 4. And so when we approach 2 from this direction, we get 4, and we approach 2 from this direction, we get 4. And if the same value is achieved when approaching 2 from either side, then we say that this limit, the answer to this question, is 4. All right, so that's how we evaluate the limits of functions. And so based on this example, we have a definition. All right, which I'll type here. So we say the limit as x approaches a for a function f of x is equal to a limit right here. We write it using this notation. So we have a definition. This is actually a definition. This is defined as follows. We can make values of f of x arbitrarily close to L by taking x to be close to A, but not equal to A. All right, so this L that I have in quotes right here in this statement is the same as this L. So we can take our output to be arbitrarily close to this number, L, as we drive as we drive x toward A from either direction. And the caveat is that x will never equal to A. Okay, so it's a limit. Okay, it's a bounded. It's not the exact value. It's a limit. Even though the use of the equality is somewhat perplexing, it is a limiting problem. All right, so we can do a fair number of examples like this. So for instance, let's consider this problem. The limit as x approaches, say, 1 for a rational function. Say x minus 1 divided by x squared minus 1. Okay, so what is this limit? How do we know what this limit is? Well, clearly, x cannot be 1 because 1 is not in the domain of f of x. So how do we deal with this? Well, the only technique that we have at this juncture would be to build a table. Okay, and again, we'll approach 1 from values of x less than 1, and we'll approach 1 from values of x greater than 1. And if the two numbers converge, then we could say we have a limit. We can try a graphical approach as well. So let's try at the outset of this problem a graphical approach. So let me pull it up on another page. So here's our problem. The limit as x approaches 1. And let's go ahead and attempt to graph this function. Insert, say, internet browser. And let me pull up the graphing calculator. Now, to graph this function, of course, you'll have to go through the procedures that we've discussed in the first 2 lectures. All right, so I'll refer you to the notes, but for convenience sake, I'm just going to go ahead and use the graphing calculator because I'm trying to demonstrate a different situation here. So our graph is y is equal to x squared, x minus 1 divided by x squared minus 1. Okay, so what does the graph look like? Oops, here we go again. This function calculator gets confused. Y is equal to x minus 1 divided by x squared minus 1. There we go. Now we have it. Okay, so the graph is this parabolic looking shape, but of course we do have a hole at x equals to what? 1. Remember, I'll leave it to you to understand why we have a hole at x equals 1. So let me zoom in. Okay, and bear in mind that we want the limit as x approaches 1. So let me go ahead and annotate the hole. So let's draw a blue circle right here. There's our hole, which the graph is not showing. So the situation is, what happens as x approaches 1? What is the limiting value? So if we approach 1 from this direction, as we get very, very close to 1, what is the output value of the function getting close to? Well, right here, it's this. And what is this value? It looks like to be roughly 0.5. Okay, so at least when we approach 1 from numbers less than 1, or we approach 1 from the left, the limit appears to be 0.5. Does the same hold when we approach 1 from numbers bigger than 1, or as we approach 1 from the right? It most certainly does. Okay, so again, we have an output of 0.5 as we get close to 1 but not equal to 1. Okay, so using this result, we can say that the answer to this limiting problem, at least insofar as the graph goes, is equal to 0.5. Okay, and we can analyze this problem tabularly as well. So let me post the table for you. All right, so let me copy the table. So here's our table right here. So look what happens. It's a little bit smeared. I apologize for that. But in this case, x less than 1. So we're approaching 1 from numbers less than x. Okay? And look at the corresponding outputs. It appears as though the outputs are converging toward 0.5 as we approach 1 from the left. Now we approach 1 from the right, from numbers bigger than 1. Okay? And look at the corresponding outputs. Again, it appears that the sequence of outputs as x gets closer to 1 becomes 0.5. So the table confirms our graphical assessment that the limit is 0.5. Even though the point 1, 0.5 is not on the graph, we do have a limit. So this is an important concept right here. Even though x equals 1 is not in the domain of f of x, the limit as x approaches 1 for f of x nevertheless exists. Okay? So a function may not exist at a particular value of x, but its limit may, as in this example. All right, so very interesting result. Now let's modify the graph. Oops, I deleted it, didn't I? I'll go back and post it again. So this time I'm going to take the same graph, y is equal to x minus 1 divided by x squared minus 1. And I'm going to define it. I'm going to give it a value at x equals 1 through a piecewise structure. So here we go. So y is equal to x minus 1 divided by x squared minus 1. Okay. And the next thing I'm going to do is I'm going to define the point 0.5, 2. So let's plot this point. Okay, so this time, this is my graph. Here's my graph. So I forced the function to actually exist at 0.5. So let me write that down as you would write it piecewise. Using piecewise notation, we have f of x is equal to, piecewise now, x minus 1 divided by x squared minus 1 if x doesn't equal to 1. All right? Otherwise, it's equal to 2. Oops, I need to make an adjustment here. I got the wrong point plotted. Let me make that 1. Okay. All right. Otherwise, it's equal to 2 if x equals to 1. All right. So let me go ahead and reinstate the discontinuity, the hole. Okay. So there's the hole, not shown on the computer graph, but we'll show it. But we did nevertheless give it a value, give the function a value at x equals to 1. So the question is then, what is the limit as x approaches 1 of f of x, where f of x is now defined piecewise? Now, f of x exists for all values of x. Okay? It just so happens that at x equals 1, the output is 2. I forced it to be 2. So every point on the x-axis has a corresponding output on the y-axis for this function. So the limit, does that alter the limit then? That's the question. Does it alter the limit? Well, you use the same ideas in evaluating the limit. In the limit, you start off with, say, for instance, values of x less than 1, and you walk along the x-axis and you examine the outputs as you get closer and closer to 1. And then you do the same thing to the right of 1. You examine the outputs of the function as you get closer and closer to 1 for numbers bigger than 1. And the result is still the same as before. The output will be 1/2 because we never reach 1. Okay? We get very close to 1, but we never reach 1. Even though the output, so this is an example of what's being illustrated here is the limit. I'll type it so it won't look so messy. What's being demonstrated here is the limit of f of x as x approaches 1 is not the same as f of 1. Okay? All right? The limit is 1/2, but f of 1 is 2. So a rather peculiar case shows up here. Okay. All right. So there's one example. Let me pin this. Let's do some more examples, because there are all kinds of unique circumstances that tell us how to deal with limits. So let me scratch this, scratch this. All right, so I'll come back to this graph. So let me add another page. Okay, so let's consider another limit for a rational function. The limit, say as t approaches 0 for this function. I'll have the square root. I forgot where the square root symbol was. The square root of, say, t squared plus 9. Okay, that's under the radical. Minus 3. Oops, that's in the numerator, sorry. Get rid of that 3. Divided by t squared. Okay. All right, so we want to calculate this limit. T approaches 0. Well, clearly, 0 is not in the domain of this function. All right? So one choice we can deal with to answer this question is we can use a tabular approach, or we can go back and attempt a graphical remedy or graphical exploration. So let's try that. Let's try a graphical approach at the outset. So we have y is equal to, in this case I'll change t to x. So we'll have t squared plus 9 to the 1/2 minus 3 Let me put this in parentheses. Oops, I have to start over, don't I? This graphical editor isn't exactly the easiest thing to work with. Okay, so y is equal to, let's try t squared, not t, x squared plus 9 to 0.5 minus 3 divided by t squared. X squared, excuse me, since it's an x. Okay. Okay, so will that work for us? Let's see. That doesn't quite work, does it? Try it again. Try typing it in again. Y is equal to x squared plus 9 to the 0.5 minus 3 divided by x squared. Okay, so the claim is that this is the graph, and so let me zoom in or zoom out or zoom in so we can see. It's almost like a straight line, isn't it? Oh, there's some interesting stuff going on around 0. Or is there? Okay, it's almost like a straight line, this graph. So it has a very linear looking property to it. Okay, so what do you think this is? So let's hover over it, and so it looks like it's going to be, say, so as we approach 0 from numbers less than 0, it looks like the output is holding steady at 0.1667. And let's say we start out here, and as we approach 0 from numbers bigger than 0, the output remains constant. Look at the ordinate. Look at the ordinate of the coordinates shown in this box. Okay, as we get closer and closer to 0, okay, and it looked like at 0 we had an undefined, right? Yeah, say 0 undefined. So there's the hole right there. Okay, so it does actually draw a hole. But it looks like this, from a graphical perspective, that the output of this function approaches 0.1667 as we get closer to 0 from either side. So this limit does exist. And then, of course, we can take a look at the tabular approach. So let me pull up the table. Now, the format of this table is rather interesting. So it might be worthwhile to go through, explain the information contained in this table. Okay, notice that the values of t are defined as plus or minus. So, and why is that? Well, it just so happens that this function is an even function. Okay, so if we plug in positive values for t, the outputs would be the same as if we plug in the negative of those positive values for t. And so that's why they have plus or minus 1. It doesn't matter what the sign of the input is. The output would stay the same. And as you can tell, as we get closer and closer to 0, using a calculator, the outputs get closer and closer to 0.1667. All right, so how would we solve this algebraically, or can we do it? That would be a very interesting question. So let's see if we can compute this without the assist of a calculator or a graphing tool. All right, so we have f of t is equal to, and I'll replace the radical with the exponential format. Okay, so I'm going to replace radical square root with exponential 1/2. Okay, and so over t squared. Now let's see if this will work. All right, now if I were to multiply this upstairs and downstairs of this rational function by the conjugate of the numerator, this is what it would look like, the multiplication. I propose that we do this. So that'll be t squared plus 9 to the 1/2 plus 3. This is the conjugate. Remember, in conjugation, you just flip the signs. And then we have to do the same to downstairs, right? T squared plus 9 to the 1/2 plus 3. All right? Now, what happens when we do this multiplication? What is the result? Well, the numerator is the product of two squares, right? So our f of t then would become t squared plus 9. I'm using FOIL now. Okay, I multiply the first two terms. The product of the first two terms would just simply be t squared plus 9 because 1/2 plus 1/2 is 1. And then the outer and inner term products would cancel, and then we're left with minus 9 divided by t squared times t squared plus 9 to the 1/2 plus 3. All right, so we're left with that. And then we can simplify the numerators. Well, the 9's cancel, right? So the 9's cancel, and then when the 9's cancel, the t squareds would correspondingly cancel as well. So after we cancel the 9's, we can cancel the t squares, and then we're left with 1 divided by t squared plus 9 to the 1/2 plus 3. Okay, and then we can go ahead and figure that this, since 0 is in the domain, of the function, and the function is continuous for all values of t, there are no holes or discontinuities in this function. We can go ahead and use what's called the direct substitution principle, what I'll talk about later. And we can say that the limit, since this function exists for all values of t, okay, we can say, because this function exists for all values of t, we can plug in t equals 0 directly. That's one caveat to taking limits. Would just equal to, and if we did that, that would be 1/6. If I plug in 0 directly. And again, this is called the substitution rule, and I'll talk about it later. So just a little bit of foreshadowing. All right, so the next problem, let's consider, next page. Let's consider an examination of a limit that doesn't involve algebraic, graphical, or tabular type approaches. So let me post one here. The limit as x approaches 0 of sine x over x. Okay. So clearly 0 is not in the domain of this function. If we plugged in 0 directly, we would of course have division by 0. So, but what happens if we get very close to 0 from either side of this function? All right. So I'm not going to graph this function yet. I'm going to do a rather interesting proof that I discovered a while back. It involves using trigonometry, and so let me go ahead and show you an illustration of how I'm going to solve this limit. I'm going to calculate this limit by construction. So let me create the figure. Okay, so let me select it. And I'll show you a rather interesting construction. Now, I don't expect you to be able to derive this construction. This construction was a long time in coming, so using your own means, I have no expectation of you're being able to derive this, but it is a rather interesting proof. All right, so here we have a circle of radius r. So you see, and here's the origin of the circle drawn in the xy plane. And I've got a couple of drawings built into this circle. Okay, the first thing that we want to notice is the inclusion of triangle OAR, which I'll outline in green. So triangle OAR. Okay, so that's one construction. Now, triangle OAR, of course, is an isosceles triangle. An isosceles triangle is a triangle that has the lengths of at least two of its sides are the same length. So in this case, the length of this leg of triangle OAR is R, and then the length of the leg OR is R. Okay. And also another thing about triangle OAR, you see this angle right here, angle theta that I'm highlighting. Angle theta subtends this arc, which I'm drawing in purple. Okay, so angle theta subtends, in other words, the rays, the two component rays that define angle theta, well, when they intersect, the two component rays intersect the circle, we say it's what's called subtends the circle, and the subtending angle is called theta. All right, and then finally what I'm going to do is I'm going to draw a perpendicular line at the point of tangency R. Okay, so we have this perpendicular line. And it's going to go shooting way up. And then what I'm going to do is, okay, I'm going to extend line segment OA. So line segment OA, I'm going to extend it out until it intersects the red line. Okay, in this top point, you can't see it, it got truncated, but it's called B. So that's point B right there. Okay, and we know that line OA will intersect line BR because the two lines are not parallel, and they both lie in the XY plane. So we know that they're going to intersect. And when they intersect, they clearly form a triangle ORB. So can you see triangle ORB? Okay, so now here's how we're going to evaluate this limit. So let me show you how this drawing construction relates to the limit problem that we're trying to solve. Well, it turns out if I let A be the area of a shape, okay, let A be the area of object, whatever. Okay, object can be a circle, it can be a triangle, it can be a rectangle, it can be a wedge. All right, so A is a function. So if I were to do this, if I were to write this, the area of triangle OAR, you see triangle OAR, it's in green, and so I'm going to write triangle OAR with a little triangle symbol before it. So the area of triangle OAR. Okay, you see it? You see it? You can kind of visualize the area of that triangle. That happens to be less than the area, okay, of sector OAR. Okay, so I'll brief you on what sector OAR is. So let me outline in purple what sector OAR is. Sector OAR is this object outlined in purple. Okay, it's that kind of wedge piece formed by the subtending angle theta. So can you see how the sector has this excess area, right? The sector OAR is the area of triangle OAR plus this little purple additional excess, right? Okay, and finally we have that the area of sector OAR, where's my cursor? Did my computer crash? Yeah, display drive, okay. So finally we have the area of sector OAR is less than the area of triangle OBR, and that's obvious from the drawing, right? Can you see triangle OBR? Okay, so just from pictures alone, we see we have this inequality relationship. Now, okay, so now here's an interesting fact. From trigonometry, we know that the sine of an angle, okay, where the angle, in this case theta, is for a right triangle, the sine of an angle in a right triangle is the length of the opposite leg divided by the hypotenuse, the length of the hypotenuse. So if you can see theta, and you see I've dropped a perpendicular line from A to segment OR, you see this perpendicular line that I've got the hash mark right here? Okay, this would be from construction opposite, which is AC, okay, divided by the length of the hypotenuse, which is OA. Okay, so look at those two line segments and convince yourself that that would be the sine of theta in radians. So that would be AC And of course, the length of OA is simply the radius of the circle. So it's AC over R. Okay, and so now we have a formula for the length of line segment AC. So AC, and I'll explain why I need this length in just a second. So AC is equal to R sine theta, just solving algebraically. That's the length of line segment AC. Okay. Now, what next? So we can compute, here's where we need AC. We can compute the area of triangle OAR in terms of theta, okay? So the area of triangle OAR is equal to 1/2 times the length of the base, which is R, times the height, which is AC. Now, how do we know that AC is the height? Well, we know that A is not on OR, and the height of the triangle is the distance from the base to this vertex A. Okay, and the distance from the base to the vertex A is, we've denoted as AC. But we have solved for AC in terms of theta. So let's go ahead and plug in our equation for AC. And so that would be R sine theta. Okay, so, and then we'll go ahead and collect terms. So that would be 1/2 R squared sine theta. Okay, so there's the area of triangle OAR in terms of theta. Convince yourself that that is the solution. Okay, now the next thing we want to do is we want to find the area of sector OAR in terms of theta. Well, this actually comes from geometry. So the area of sector OAR, and I'll put a little curvy line above it to denote sector, to indicate that we're not dealing with the area of a triangle. This is a definition, okay? So the area of a sector, okay, where theta is the inscribed angle, or the subtending angle that is, would be simply 1/2 R squared theta. Okay, so this result comes from trigonometry. Okay? And now next we need to calculate, say, the area of triangle OBR. Okay, triangle OBR, it's the big triangle shown here, in terms of theta. All right, so before we do that, we can surmise that the tangent of theta okay, so to calculate the area of triangle OBR in terms of theta, I need to get theta as an expression of one of these geometric objects shown in the picture. And so as an assist, we know that the tangent of theta is opposite over adjacent. So that would be BR divided by OR. Can you see that? Opposite over adjacent for theta. Now, and then of course we know that OR is simply the radius of the circle. So that would be BR times R. And we know that BR is the height of triangle OBR. So the height of triangle OBR is simply BR, and that's equal to R tan theta. Okay, so you can see that from the picture. I'm hoping that you're able to recall enough trigonometry to understand these fundamental ideas. Okay, so now let's calculate the area of triangle OBR. So the area of triangle OBR is equal to 1/2 the base length, which is R, times the height, which is BR. Okay, and now we'll plug in the expression for BR. Since we know that BR is a function of theta, we know that the area then of triangle OBR is a function of theta. So that would be R times R tan theta. Okay, because BR comes from here. That's all I did as I substituted. Okay, so we have we can now recast our inequality, our original inequality in terms of theta. So let me extend the page. Okay, so I'm going to take this inequality right here. The inequality that involved the areas of the three objects under consideration, and I'll rewrite this inequality in terms of theta. So we have, based on the illustration, we have 1/2 r squared sine theta, which is the area of the smaller rectangle, is less than the area of the sector, which is 1/2 r squared theta, which is less than the area of the big triangle, which is 1/2 r squared tan theta. Okay, now since r is not 0, we can cancel out the common terms of this inequality and still retain the inequality. So let's do that. So if I cancel 1/2 r squared from each of the terms in the inequality, I'm left with sine theta is less than theta is less than tan theta. Okay, so we have this. And all three quantities in this inequality are, of course, greater than 0. Because, why is that? Because we're dealing with quadrant 1 values. And tan theta is greater than 0 in quadrant 1, and sine theta is greater than 0 in quadrant 1, and theta, of course, is greater than 0 in quadrant 1. So all three quantities are positive. So that will have ramifications as we seek to evaluate our limit. So I'm going to take this inequality, and I'm going to divide all of the terms in this inequality by sine theta. So we assume that theta is not 0. So if theta is not 0, sine theta is not 0. So if I do that, if I sweep through and I divide everybody by sine theta, I get this. Now recall what the definition of tan is. Okay, do you remember what tangent theta is? So tangent theta is sine theta over cosine theta, by definition. Okay, now if I were to take tangent theta and divide it by sine theta, I'll be left with 1 over cosine theta. Okay, so I have that. Okay. All right, so the next thing I'm going to do is I'm going to take this inequality, and I'm going to take the reciprocals of each terms in the inequality. Now, because of the ordering of this inequality, the terms grow larger as we move to the right in this inequality. If I were to take the reciprocals of each of the terms, I'll have to flip the direction of the inequality. So I'm going to flip the direction. Okay, and a very significant term pops out when I transform this inequality. I have this. I have this result. Okay, so now what happens? All right, so what do I do next? Well, the next thing I'm going to do is I'm going to take the limit as theta approaches 0 of the entire inequality. Okay, and one of the things I'm about to show you would be the, we'll discuss in the next section, would be the so-called limit laws. So, but for now, what I can do is I can take this limit operator and I can distribute it to each term participating in this inequality chain. So simplifying this expression, I can say this. Okay. Now, let's look at the limit as theta approaches 0 of 1. All right, so if I were to graph, here's 1, right, and then here's my theta axis. Here's my output. Clearly, as theta approaches 0 from either side for this graph, the output is going to be 1. So this is an important limit concept. The limit of a constant is always the constant itself. Okay, so it's kind of a trivial fact. So we can simplify this limit by saying that this is just 1. And look at the middle term of this chain of inequalities. Okay, this is the quantity we're trying to compute. We actually want this. All right, and this is what we don't know. So do we have a problem here? Well, maybe not. So we need to calculate the limit as theta approaches 0 for cosine theta, and we can probably do that graphically. So let's hop to our graph. Let me delete this. And we'll say y is equal to, let me. So let's say y is equal to, what's going on here? Why is it stuck on? Hello. Y is equal to cosine x. Okay, and here we have our cosine function, and we're interested in what happens as x, or in this case theta, approaches 0 from either direction. So we can just walk it, right? So here we have, as we get closer and closer to 0 from the left, from values of theta less than 0, look what the output becomes. So it becomes 1, okay, as we get closer and closer to 0 from the left. Do we get the same result as we get closer and closer to theta equals 0 from the right? Well, yeah. Look at the ordinates of the points in the bounding box. It appears to be closer and closer to 1. So we can conclude then that the limit as theta approaches 0 of cosine theta is 1 as well, just from a graphical depiction. All right. So now look at this result. We have, what I'm circling is what we want. Now, the limit of what we want is less than 1, and it's greater than 1. So what does that mean? Does that mean that the limit doesn't exist? In fact, it doesn't. In fact, it does mean that this limit exists. Right? This is an example of what's called the squeeze theorem. Okay? The squeeze theorem. And I think there's an error in my notes. I think I have this written as 1. That should be 0. And so by the squeeze theorem, if the quantity is less than 1 and greater than 1 at the same time, then it must be that quantity 1. So by the squeeze theorem, this limit is 1. And that's why I wanted to show you this proof, because it's an example of a very famous mathematical technique called the squeeze theorem. All right, so a rather roundabout way of showing what this is. Okay. So it served as kind of a review for treatment of inequalities, the squeeze theorem, and some trigonometric constructions. And of course, we can always draw the graph. Now the graph should have a hole at theta equals 0, and we can always use a table to draw the graph as well. But just as a sanity check, we'll go ahead and draw the graph. Plot the graph, that is. Okay, so we have y is equal to sine x divided by x. Okay, and we'll zoom in. So here's sine x over x, and we're interested in what happens as we get towards 0 from either side. So we'll start off, say, here, and we'll walk along the graph and look at the outputs. See, 0.9967. So as we get closer and closer to 0, and of course 0 at x equals 0, it's undefined. there's a hole, okay, and as we walk toward x equals 0 from numbers bigger than 0, look at the output. Look at the ordinates of what's in the box. Illustrate it in the box, and then finally we hit undefined. So the limit, so as we approach 0 from this direction, the output goes to 1. And as we approach 0 from this direction, the output goes to 1. And then when we hit 0, there is no output. The function is undefined. So this is a case where the limit exists at a particular value of the limit exists for a particular value of x, namely 0, but the function has no output for x equals 0. Okay. All right, so this is one limit that you probably should memorize, because we'll see it. It has some very useful applications, and we'll see it again. Okay, so, all right, so next topic, an interesting proof. So how about cases where a function may not have a limiting value? So we need to complete our discussion with, say, something that looks like this. Consider this function. Y is equal to, come on, calculator, cooperate. Y is equal to y, come on, y is equal to sine of pi over x. Okay, so a rather interesting graph. And we want to examine what the limit is. So the problem here is, what is the limit as x approaches 0 of sine of pi over x? Well, obviously 0 is not in the domain of this function, okay? Because you can't divide by 0. And here's the graph. So maybe if we just zoomed in, we can ascertain the result. Okay, we can trace along the curve as we zoom in. But look what happens as we zoom in. Look, the graph is actually a pretty solid fill. Okay, there's nothing here to grab hold of to trace the graph. And that's because what's happening is, as we get closer to 0, the output of this function ranges very erratically from -1 to 1. And that's what this solid fill is indicating. So in other words, if I were to say walk close to 0 in this direction, okay, my outputs are going to change. They're going to sway from, or swing from -1 to 1. And so there's no consistent number that leads to a definitive output. All right. So you could say, well, I'm close here. Say I'm close to a number as I go in this direction, but I could be going in this direction and get close, and my number will not match your number. So in other words, in this case, the left limit approach does not equal to the right limit approach. That would be the case of this function. And we can discuss mathematically why that would happen. It's a rather interesting proof, so let's try and, it's somewhat complicated. You won't be responsible for it on any exams, but the understanding of this technique is rather insightful. So let me type in why this is the case. So again, so the limit as x approaches 0 for sine pi over x does not exist. All right? And here's why. Here's the explanation. As x approaches 0, okay, what happens to pi over x? Pi over x approaches infinity. Right? Because as x grows smaller and smaller, pi divided by a tiny number goes to infinity. Okay, so thus, in any open interval containing 0, okay, y'all know what I mean by an open interval containing 0? Let me show you. So here's an open interval. Here's 0 on my x-axis. Here's my x-axis. and I say any open interval, so containing 0. So open interval is denoted from your algebra experience by open parentheses. So if I choose any interval on the x-axis and it contains 0, what happens? All right, so in any open interval containing 0, I can find my text box. There will be values of x such that pi over x is a multiple of 2 pi. Okay? In other words, in this open interval right here, I can find a value of x, or actually an infinite number of values of x, so that when I plug it into pi over x, I'll get some multiple of 2 pi. Okay? So in particular, if I say x, so if I choose x to be, say, 1 over 2 pi squared, okay? So plug in 1 over 2 pi squared. If I were to do that, or how about it, say x equals to a half, okay? If x equals to a half, pi divided by a half is 2 pi. How about x equals to a quarter? Pi divided by a quarter is 4 pi. So there are an infinite number of values of choices of x that I can choose. Okay, so so you understand this. So likewise, okay, there are values of x in this interval such that pi over x is pi over 2 more than a multiple of 2 pi. Okay, so I can find a value of x in this interval such that pi over x is equal to, say, 7 pi over 2 or 11 pi over 2. Okay, convince yourself that that's the case. Furthermore, there are values of x in this open interval such that pi over x is 3 pi over 2 more than a multiple of 2 pi. All right, and convince yourself. So yeah, so I could have 9 pi over 2, 12, or 15 pi over 2, or 21 pi over 2. So I can find values of x that generate those kinds of outputs for pi over x. Now, the sign of those values are 0, 1, and -1, respectively. Okay? So sine of pi over x oscillates an infinite number of times between -1 and 1 in any neighborhood of 0. Okay, and you can, because you can always find these x values that generate output pi over x of being 2 pi, or a multiple of 2 pi, or pi halves plus a multiple of 2 pi, or 3 pi over 2 plus a multiple of 2 pi. Convince yourself that you can find an infinite number of x values that would generate this. Okay, so the conclusion is, thus, the limit as x approaches 0 of sine pi over x does not exist, because we can't corral the value. All right. Okay, so an interesting structure there. All right. Next slide. So, other types of limits. Okay. The next type of limit we're going to be talking about are one-sided limits. So what are one-sided limits? Let me go back to my graphing calculator. Let me get rid of this. Let me erase this structure. And let's say we have a function, a piecewise defined function, say h of t. So we say h is equal to 0 if t less than 0, right? And h is equal to 1 for t greater than or equal to 0. Okay, so this is a piecewise defined function, and let's look at it. So the function h is the combination of the red and blue curves. Now the question is, what is the limit as t approaches 0? So let me write that down for you. So we want to examine the limit as t approaches 0 of h of t. And this is the graph of h of t. All right. So clearly, as we walk along the graph, okay, you see the output? So as I walk along towards 0, I mean, my t values are approaching 0 from the left. The output is held steady at 0. Okay, and of course at 0 the output is undefined because, well, let's go ahead and define a value. Let me see if I can modify this. Equals. Oops. Will it let me? Okay, yeah, I think it'll let me. Okay, good. So, oops, let me zoom out so I can see all of the graph. All right, so let's do our walk again. Let's go for a walk, right? Okay, so as I walk along the t-axis and I'm approaching 0, then I hit 0 and it's still undefined. Okay, yeah, it's still undefined. Okay, so, but nevertheless, as I get closer and closer to 0 from the left, my output is 0. Now let's go for a walk for values of t greater than 0. So as I approach 0, my outputs are held at 1. Okay, and when I hit t equals 0, the output here, at least insofar as the blue curve goes, is 1. All right, so now how about the limit? Well, a couple of different structures are emerging here. We can say that there are two types of limits going on here. One of which is this. We can write this. The limit as t approaches 0 from numbers smaller than 0 can be written this way with a little minus superscript for the a, which is 0. All right, and what this means is that we're approaching 0 from numbers less than 0. And so as we track the graph, we discovered that that was 0. All right, now we had another kind of limit, and that was the limit as t approaches 0 from numbers bigger than t. And the way we would write that is using a superscript plus. And we discovered that that was equal to 1. Okay. And just for good measure, I'll go ahead and write h of t piecewise. Here's how you would write h of t as a piecewise defined function. So it's equal to 0 for t less than 0, and it's equal to 1 for t greater than or equal to 0. Okay, so there's the piecewise definition. And notice that the left limit, this is called the left limit right here. And this is called the right limit for obvious reasons. Okay, so understand these two different types of limits. All right, and that brings up an important theorem, okay, which I'll write here. So that was a discussion on one-sided limits. I can take this box away. Okay, an important theorem, something that you'll have to memorize, is the limit, okay, as x approaches a, for a function f of x exists. Or if it exists, it's going to equal to a number. Remember, a limit always equals to a number, a distinct number, if and only if the left-hand limit is equal to the right-hand limit. If and only if the limit as x approaches a from the left of the function is equal to L, and the limit as x approaches a from numbers bigger than a for the function is equal to L. Okay. All right. So basically, if you read this statement forward, you can also read it backwards, because that's what if and only if allows us. So if this condition is true, then this condition is true. If this condition is true, then this condition is true. All right. So the converse is also true. Okay, so let's go back to that graph again of the piecewise defined function. Let me see if I can find it. Is this it? Now, in the case of this graph, I guess I'll have to redraw it. H is equal to 0 for t less than 0. H is equal to 1 for t greater than or equal to 0. So in the case of this graph, we have that the left limit was 0 and the right limit was 1. So that means that the left and right limits are not the same. And so consequently, the limit as t approaches 0, based on that theorem I just gave you, the limit as t approaches 0 of h of t does not exist, because the left and right limits are not the same. Okay, so that's a very important concept. And there's an illustration in the online notes. All right, so I think we're ready to work a couple of examples. See how many examples? Maybe, how many do I have? Oh, I just have one example. Okay. no, actually a couple examples. One graph with a multi-part question associated with it. So let me post an example. Okay, so let me pull up the graph that I want to ask a question about. And I believe this graph is in your text, if you have a copy of the text. So let's consider now y equals g of x. And I'm not giving you any numbers for g of x. It's just a relation, a functional relation, where the output. So let me accentuate so you can see it better, because it may not show up very well on YouTube. So we have this arc right here. And then we have a hole right here. And then we have a hole right here. And then it goes like this. So some hypothetical graph. We haven't defined it numerically. And then we have a value at x equals 5 right there. All right. So the question is, the first question of a multi-part question is, what is the limit as x approaches 2 from numbers smaller than 2 of g of x? Well, we can read this from the graph, okay? So we're approaching 2 in this direction. And as we get closer and closer to x equals 2, the output appears to be 3. So for all intents and purposes, we could say it's 3. Now what's interesting about this function is g of 2, okay, g of x evaluated at x equals 2 is not defined, okay? There's no functional value output at g of x equals 2, but the limit exists. At least the left limit exists. It's 3, okay? So note that. Now, how about the limit as x approaches 2 from numbers bigger than 2 of g of x? All right? Well, that can be obtained by just walking along the graph. Okay, so we walk along the graph in this direction, and we note that the output gets closer and closer to 1. So that's 1. All right. So clearly, the left limit does not equal to the right limit. And so what kind of conclusion can we draw? Well, we say that the limit as x approaches 2 of g of x does not exist. Not only does the limit not exist, but the function is not defined at 2. All right. Okay, very interesting. So let's consider the case now as x approaches 5 from both directions. So the question I'm asking now is, what is the limit as x approaches 5 from the left of 5 of g of x? All right, so we'll read it from the graph. So as we approach 5 from numbers less than 5, the output appears to be going to 2, right? We'll say that's 2. We'll call that 2, okay? So let's just say it's 2, just reading from the graph. And the limit as x approaches 5 from numbers bigger than 5, well, that appears to be 2 as well. Okay, and so the takeaway is the limit as x approaches 2 of g of x is 2. Not 2, 5, excuse me, that should be 5, sorry. That should be 5. Okay, So the limit exists for this, but what is g of 5 anyway? G of 5 is equal to, it appears to be 1. Somewhere around 1, right? So here's a case where the limit of a function is not the same as the function evaluated at the limiting value a, okay? The limit as x approaches 5 of g of x is 2, but g of 5 is 1. So we run into these interesting cases. All right. So another topic I want to deal with respect to limits would be the notions of infinite limits. So let's talk about infinite limits. All right. So the question I want to ask next is this. We want to evaluate this limit. The limit as x approaches 0 of this function right here. 1 divided by x squared. What is that? Can we find this? Right. So let's take a graphical approach. Let's take a graphical approach. So let me go back to the graphing calculator I had right here. So I don't think we need this anymore. So yeah, we'll go ahead and erase all of the markups here. Let me erase this. This is another problem, so I can erase all of this. And I want to graph the function y is equal to 1 over x squared. Okay, and it's shown in red here. And so the question is, what is the limit? Okay, so let me pull back the problem. Let me copy. Oops, when I do that, I probably lose my graph, don't I? Okay, well, I'll pull it back. So what was it? What page was it on? This one, right? So we're evaluating this limit. Okay, so y is equal to 1 over x squared. Oops. 1 divided by x squared. Okay, so there we have it, shown in red again. Now, so what we can do is we can trace. We can zoom out, and we can go for a walk. So let's approach 0 from the left. All right, so notice that as I approach 0, look at my corresponding output values. Okay, my x values are getting closer. Look at the abscissas. They're getting closer and closer to 0, right? And look at the output values. They're getting larger and larger. Let me zoom out some more. Watch what happens. Okay, the output gets bigger and bigger as I approach 0 from the left. So that means that my output is approaching infinity as x approaches 0 from the left. All right, now let's approach 0 from the right. It's too restrictive there. All right. So as I approach 0 from the right, so as my x values get smaller and smaller, look at my outputs. My output values get bigger and bigger. So as I approach 0 from the right, the output goes to infinity. So my left limit is infinity and my right limit is infinity. So we actually say that then the limit as x approaches 0 can be stated to be infinity. So infinity can be a plausible result for limit problems. Okay, so just be conscientious of that. And if necessary, we can use a table to demonstrate this concept even more. Let me post a table. Now 1 over x squared is an even function. Okay, so let's plug in some values. So here's a table for 1 over x squared. And look, as x goes smaller and smaller from either direction on either side of 0, look at the output. It grows very, very large. So there's a demonstration of an infinite limit. Okay, so a couple more pictures I want to show you. Okay, so we've solved this problem. Some conceptual drawings, that is. So in this drawing, the limit as x approaches a number goes to infinity for this particular function. So can you readily see, as x approaches a from either side, the output goes to infinity. And what is the criteria for that to happen? Okay, in order for this statement, for this limit to hold, we need basically a vertical asymptote right here. So x equals a is a vertical asymptote. And so what we've got here, basically this statement right here, this is the definition of a vertical asymptote. Okay? In fact, that is the definition of a vertical asymptote. X is a vertical asymptote, or x equals a is a vertical asymptote if and only if, which I write as IFF, the limit as x approaches a of f of x is equal to infinity. That's the definition. Or minus infinity. Okay, so that is how you define a vertical asymptote. Let me show you the minus infinity case. Here's the minus infinity case. Oops, erase. So look at this drawing. As x approaches a from either side, the output goes to minus infinity. And so x equals a, again, is a vertical asymptote. All right. There are other examples of vertical asymptotes. You don't need two-sided limits to have the presence of a vertical asymptote. There are some strange cases where a one-sided limit is sufficient for the presence of a vertical asymptote. So let me see if I can pull up another demonstration. Yeah, let me pull these figures. So vertical asymptotes can be determined by one-sided limits as well, as shown in this illustration. So in figure A, note that x approaches a, the output goes to infinity. So x equals a is a vertical asymptote. So here's a vertical asymptote, even though the function is not defined for x greater than a. In this figure, as x approaches a plus, okay, this is x approaches a minus. Okay, it's kind of hard to read there. Here, x approaches a plus. Okay, as x approaches a plus, okay, the output goes to positive infinity. And here we have x approaches a minus. The output goes to minus infinity. Okay, and as here as x approaches a plus, the output goes to minus infinity. So one-sided limits can result in infinity or minus infinity outputs as well. Right, so and those are all, of course, the definitions of vertical asymptotes. Okay, so let me do another graphical example. go back to my graphing chart. If I can find it. Where was it? Which slide was it on? This one? Yeah, here we go. Okay. So let me erase this content and draw another graph. So let's consider 2x divided by x minus 3. Oops, I forgot to, I'm on the wrong mode here. Okay, so y is equal to 2x divided by x minus 3. So in this case, we have a vertical asymptote at x equals 3. So let me just go ahead and draw that. X equals 3. So I'll illustrate that. X equals 3 is a VA. And this is a hyperbola, right? Okay. And so what happens as we approach 3 from numbers less than 3? Where does the output end up? Well, in this case, the output ends up at going toward minus infinity, right? It drops off toward minus infinity as we approach 3 from numbers less than 3. See, as my abscissa gets bigger, the output gets smaller and smaller. And by smaller and smaller, I mean it goes toward negative infinity. Likewise, as my abscissa approaches 3 from numbers bigger than 3, in other words, my abscissa is getting smaller and smaller, look what's happening to my outputs. My outputs are going bigger and bigger and bigger and bigger. Eventually it shoots up toward infinity. So in this case, the left and right limits are not the same. And so the limit as x approach, okay, so an important takeaway is we have the limit as x approaches 3 from numbers smaller than 3 of 2x over x minus 3 is equal to minus infinity. Okay, and then the limit, so that limit is said to exist, or minus infinity, and the limit as x approaches 3 plus of 2x over x minus 3 is equal to infinity. And these two limits are not the same. So therefore, the takeaway is the limit as x approaches 3 of 2x over x minus 3 does not exist. But the left and right limits do exist. Okay. We can do another example. Say, how about, let's plot the tangent function. Okay, so I'm going to erase this now. And dismiss. Let's go back to my dismiss this, dismiss this. And so I'm going to say plot y is equal to tangent of x. Okay, and let's say, let me set my window properties so that the x-axis is in terms of pi. So let's do this. Okay. And let's just say negative 5 pi over 2 less than or equal to x less than or equal to 5 pi over 2. So let's just plot the tan function on this interval. And the question is, we want to analyze the limit as x approaches pi halves from numbers smaller than pi halves of the tan function. So what is this limit? What do you think this is going to be? Well, we can trace the graph. So where is pi halves? So pi halves, this is pi right here. So pi halves would be right here. Okay, so as x approaches pi halves from numbers smaller than pi halves, look what happens to the output. Well, let me go ahead and just plot y equals pi halves, right? So y is equal to, no, x is equal to pi halves. So let's put some perspective here. Oh, what happened? Typo, huh? Okay, so let's put that back, and x is equal to pi over 2. All right, so that would be shown in orange. So not showing my green curve anymore. I have to replot. All right, shoot. All right, so there's x equals pi halves, and then my next graph, y is equal to, sorry, I have to redraw it. Negative 5 pi over 2 less than or equal to x less than or equal to 5 pi over 2. All right, so there we go. Shown in black now. Okay, so as we approach pi halves, which is the orange line, from the left, look what happens to our output. The output zooms up toward infinity, right? Okay. And as we approach pi halves from numbers bigger than pi halves, the output falls toward minus infinity. Okay. So pi halves is a vertical asymptote. So the tangent function, of course, is not defined at x equals pi halves, nor does the limit exist as x approaches pi halves. But the left limit is plus infinity, and the right limit is negative infinity. Okay, so we do have that takeaway for the tangent function. All right, let's consider the natural log function. So let's plot the natural log. So y is equal to natural log of x. And that will be shown in red here. Now, clearly x has to be greater than 0 for the natural log function. So what happens as x approaches 0, effectively, we can't say, well, we can't say this for the natural log function. Technically, this is wrong. The limit as x approaches 0 of natural log of x. Technically speaking, that does not exist. And why is that? Because we cannot approach 0. We do not have a left limit, right? In order to have this limit to exist, we have to have a left and right limits being the same value. So this is absurd for the natural log function. The limit as x approaches 0 from numbers less than 0 of the natural log function. Since this doesn't exist, then the limit as x approaches 0 of the natural log function doesn't exist. But we do have a right limit. We do have this. We can approach 0 from numbers bigger than 0. That exists. So the natural log function is indeed a strange function. So what is this limit as x approaches 0 from the right? What happens? We go off the deep end, right? We go plunging down to the bottom of the ocean. We go toward negative infinity. Okay, so there's the limit for the natural log function. Okay, so that is it for section 2.2, or lecture 2 part 2. The next section we'll be discussing, lecture 2 part 3, will be regarding the limit laws. So at this point, you should be tackling some of your chapter 2 WebAssign problems. And let me think. You don't have enough material yet to start the chapter 2 project. But after the next lecture or two, you should. Okay. End of lecture.